Welcome to Module 52 on attention mechanisms and self-attention. This is going to be yet another very important module in our course, and it's going to provide a very important foundational bridge between the recurrent neural networks, which we've used recently to describe sequences, towards the architecture of transformers, which underpin a lot of the foundational models we see today. So by the end of this module, you ought to be able to explain why we're even using attention mechanisms in the first place. What do they provide that recurrent neural networks on their own don't? We're going to introduce at least 5 new terms: queries, keys, values, scores, and attention weights. These are very simple concepts, and they all relate to one another. We're going to introduce them, and you ought to be able to define them. We're going to, at a high level, talk about cross-attention versus self-attention. These are almost identical concepts, but they're slightly different, so you're going to have to be able to distinguish between them. We should be able to compare self-attention with recurrent models through experiments. We're going to see some examples. And you ought to be able to interpret the kinds of patterns you get from attention critically and cautiously, using the same sort of scientific curiosity we've been emphasizing throughout this whole course. So, we've been looking at encoder-decoder models in previous recurrent neural networks. One example of this was we'd have an input sequence made up of words in one language, like je suis étudiant, 3 words. And we would use a recurrent neural network like we see down here. Every word would be represented in some hidden vector h sub I, and then there'd be connections from one hidden vector to the next over time. And this hidden vector would gradually accumulate information from the current word and the previous context, until at the end we'd have a fixed size vector, a representation of the entire sentence C, that this encoder would have encoded all the information about this sentence. And then we would use another recurrent neural network called a decoder to unpack information in this fixed size context vector one at a time. All right, so we've encoded the information in the French sentence, and then we decode the information into producing an English sentence, I am a student, and then the hidden vector S sub I now would have sort of a representation of the previous words written out, as well as the information in the French sentence, and then it would just produce one English word at a time. So this is very vanilla, very high level. This is an encoder-decoder recurrent neural network. And the encoder had to have compressed everything into this single fixed size context vector. And quite frankly, it did a quite good job of it also, but there are some challenges here. So, I mean, this can work for short inputs, like je suis étudiant. This is only 3 words of input and 4 words of output. But if you have very, very long sequences, or very information-dense sequences, then this can become a problem for many reasons. You're basically trying to pack in a lot of information into a very reduced space. So this is a bottleneck. This fixed size context becomes a bottleneck that will end up being a challenge for us. So what we want to do is maybe reframe the question a little bit. The question should be, when we're producing the next output token, when we're writing like the current English word as the English translation of the French sentence, can we somehow connect the decoder, this output, back to the input somehow, so that we can keep on checking, our source, and then by checking the source and what words were in the source, this is going to help us with our word-by-word output translation. So instead of trying to rely on one packed summary, this fixed size, we should be able to look at the original and consult it as we go. That's the key insight and the key question we're asking right now. So let's scaffold our concepts. So we're going to change this question. Again, so just making sure this is understood, the recurrent view from the recurrent neural networks is that a single rolling state has to carry everything forward. So the hidden state at h sub t is a function of the hidden state at the previous point in time and the current word being read or being output, depending on what, if you're an encoder or decoder. And then when you're writing out your outputs, you're making your predictions, that's y hat. there's some function g, which is a function of the last hidden vector at time big T. That vector is called h sub big T, right? So that's more or less what we saw just a second ago. It's this C is basically the last hidden vector from the encoder sequence. So again, this is a bottleneck. All of the relevant information that we need at a particular point where we're now producing words, we're decoding. At a certain point in time, it might be helpful to look way back at the beginning of the sequence and not have to only have like the current status of the system. We want to be able to go back into the original sequence and look back to the very beginning of a very long sequence potentially and pull information from that. While we're doing inference, while we're doing decoding, the production of English outputs. When we're learning, again, there's a lot of connections through this computational graph, and we're going to have gradients. We need to push back through the decoder and the encoder. And as we've seen several times in this class, as you have many, many connections, and you're trying to multiply all these gradients together, if some of them go close to 0 or far away from 1, you can have instability or you can have vanishing gradients, and that's a problem also. And indeed, while we're producing the outputs, every time we produce an output, maybe the relevant information in the input sequence could have occurred at different times. It could have occurred at the beginning, the middle, or the end of the sequence. It's really kind of arbitrary in general. So we want to be able to kind of almost random access the input sequence. And then if we can access the right parts of the input sequence, that's going to help us to decode the right English word to output at this particular moment in time using this machine translation metaphor for the moment. So with attention, what we want is we want to, instead of getting a single summary, like this is all the information of the French sentence is here in this vector, now you go ahead and decode it. What we want is the current computation right now to know what it's doing and to realize what earlier representations from the French sentence are most relevant to what we need, and then we're going to pay attention to those earlier representations on purpose in order to, basically relax the idea that we have to summarize everything once and for all, and then we need to use that summary for all of our decisions going forward. So we don't want that. We want to relax. We want to be able to consult the input. So we can imagine when we're doing decoding, when we're producing our outputs of this machine translation process, we want to look back at our source states. Imagine we're going to produce the next token, or we want to translate the next token of target. So we want to produce an English word in our machine translation system. The current decoder state should be able to consult everything, all of the encoder states. It shouldn't just have the fixed context vector we called C a moment ago. So in other words, the model should be able to decide at every step, at every word it's producing, which source positions matter the most. And then visually it might look like this. We have the word je, this produced some hidden context vector h sub 1. Suis, that's produced some other context vector h sub 2. Étudiant, it produced h sub 3. So now we're producing an English word. Which of these three states, je suis étudiant, is most relevant to me, right? So I'm going to produce a particular word. Maybe one of these words matters more than the other to my English translation. So again, not all of these sources should matter equally, right? Maybe je is more important, maybe suis is more important, depending on where I am in the English sentence I'm producing. So looking back over everything and making every single word of context equally important to me is not good. I want to be able to select one or the other. I want to focus a little bit more on one word or its representation or another. So for a particular output step, different source positions, different French words should matter more or less, and therefore they should receive larger weights than others. And this is the kind of the key intuition behind the whole attention mechanism. We're going to compare what we need right now. So right now I'm calling it the current need. So I need some information. There's some information that's useful in either positions 1, 2, or 3. I'm going to weight each of these positions, 1, 2, and 3. Maybe 1 is not very important to my current need. Maybe 2 is very important, and maybe 3 is not that important either. So I'm going to weight each of these 3 input positions. and then I'll blend them together, right? So there's some information in each of these positions. I'm not going to like select only one of those positions. It's not a choice I'm making. I'm going to, because of the weights I just mentioned, I'm going to take a little bit of information from position 1, but not too much. I'll take a little bit of information from the third position, but not too much. I'll take a lot of information from the second position, which I've weighted as being important, and I'll blend all that information together somehow, and then that will be a new representation that's useful for me right now when I'm producing the current word. So high level, this is what we're aiming for. This comes from this paper, which is one of several classic foundational papers in this area. Again, just like our example, an early use of attention in recurrent neural networks was machine translation. And this exact example comes from this paper. This image comes from this very nice website. So click on this website. This is actually interactive. It doesn't tell you that much, but it's very pretty. It's a very good website apart from these graphs for you to look into. So we want something like this. We have a source over here on top with these B's. These are the input French words. And again, we have an encoder sequence going. Sorry, my bad. In this case, they're taking in English words and they're translating it into French. So the input source is English. It's a bit complicated here because here there's bidirectional connections, which we didn't really get into before. But it's still a recurrent neural network. There's just a feed forward layers, forward in time and backwards in time also. But this is just a recurrent neural network. And you have representations for the agreement on the European economic, etc. And all of this information is encoded within these hidden vectors, here just represented as these A's. That's the encoder. The decoder is producing the French translation of this English sentence. So you have le, accord, sur, la, zone, and so on. And what we kind of want is to draw connections between these words, right? So you can kind of see here the thickness of these lines represents some kind of connection between words. So agreement and accord, they literally translate very closely. If you look up an English-French dictionary, these words might be translations of one another. We don't want literally word-to-word translations because that ignores all kinds of contextual and unique ordering differences in different languages. So it's not just a lookup table. We read an English word, we look it up in a table and produce a French word. It's way too simple. But there are connections. And again, over here, European economic area gets translated as a phrase into zone économique européenne. And you can kind of see there's connections over here between European and Européenne. Area and zone have a very strong connection relative to other words. So high level, you see what's going on here, right? So there's two recurrent neural networks for encoding and decoding, respectively. And then there's now all these connections between them, between individual words, saying when you're producing this word in French, zone, this word in English, area, is more important to your translation. It's more relevant to you right now. So pay attention to the representation for the word area in the source. In this exact same paper, they showed the thickness of these lines, the amount of connections between them, can be represented in a matrix form. So here's just a matrix form of what we just saw before. You can see how there's a lot of connection between Européen and European, as indicated by this bright pixel in this matrix connecting these input French words on the rows and the output English words as columns. I get that reversed. The input is English, the output is French, but you get the idea. So just a quick side note, we're mostly going to be looking at machine translation because for simplicity, but the same concept applies to other domains as well, in particular speech recognition. This is yet another foundational paper in speech recognition, listen, attend, and spell. So here we have the inputs in the source recurrent neural network. You can see over here, it's reading frames of speech, these small 16 millisecond, usually little sections of audio. And you're reading them one at a time, and you're accumulating a hidden vector here in this recurrent neural network heading towards the right. This is an encoder, just as before. The decoder is going to produce things called or in this case it's letters. There could be phonemes also, which is related to letters. In English anyway. So H-O-W space M-U-C-H. This is another recurrent neural network. This is a decoder that reads in a hidden context vector and then produces one piece of output at a time. So instead of reading English words and printing out French words or vice versa, we're reading in acoustics and printing out letters in English. But once again, you can see there's kind of an attention going on here. So there's a big attention here from the letter H down to this particular frame over here. And indeed, this is called a spectrogram. This is a representation of audio. When I'm producing the sound H, there's a lot of attention being paid to this particular part of the input audio sequence. It kind of makes sense for those who know spectrograms. This looks a bit noisy because of the aspirant sound. Anyway, this is also from the same website. This is this visualization. So, big concept. We just have two recurrent neural networks: an encoder that encodes information, and a decoder that decodes it. But also now we're going to have these kind of these skip connections. Skip connections might be the wrong word, but shortcuts, I guess, between states of the decoder on the output and particular states of the input encoder on the input. So let's name some of these things. So we talked at the very beginning, we're going to introduce the idea of queries, keys, and values. Okay, so a query basically represents what the current computation needs. So at a particular moment in the decoding and the output, if we want to know what do I need right now in order to produce my output. The keys are going to tell us where to look. Like out of all the input tokens or states, which positions have the most information, the information that I'm looking for. And then the values will be sort of representations of those hidden vectors, the information I actually want to retrieve. And then we're going to combine them all together. So the query says I'll need a little bit of 1, a lot of 2, and a little bit of 3. We'll get the values, the actual hidden states in those encoding vectors at each of those moments in time. And then we're going to combine them all together. Then we're going to combine the information of values 1, 2, and 3 according to some kind of weighting that we've obtained in these 3 positions. I want to mention that this might be a little bit misleading. Like we, the community uses the term keys and values, and it sounds a lot like a database, and therefore it sounds like, you know, we're literally going to get discrete atomic facts as if from a table, and then we're going to just sort of combine them in deterministic kind of modular ways. And that's not the case exactly. The idea is the same, but like we've seen several times in this class, including in like expectation maximization, normally we have these sort of blends of information. So it's like a weighted combination of vectors, of numbers, and those numbers somehow represent information in some way. So even though we're talking about things as if we're like literally looking up information in a database or a dictionary, what's actually happening here is combinations of soft vectors in a soft way. So how do we do this blending? It is mathematically here. So we have the 3 concepts. We have the query vector, which is this d-dimensional vector of real valued numbers. We have keys. So if we have a key for each of our big T elements of our input. We have values. These are sort of the hidden state information, v sub 1 to v sub big T. So we have 1 for every piece of input. We'll have a scoring function, first of all, that will compare the query, like a representation of what we need right now, Q. We'll compare it to each of those big T positions, each of those keys. And this will give us a score saying, you know, how relevant is each of those input positions to what I need right now. Those scores can be really unnormalized, so we normalize it through the softmax function. We've seen this before in this class. The softmax function is a sort of a proportion of like e to the quantity, in this case the score, s sub I. This I should be inside this bracket over here, I'm sorry. I'll fix that before I post the slides if I recall. Anyways, it's like how much, like it's a weighted combination of how much of the score for position I is the component of all of the scores over all of the positions from the beginning j equals 1 to the end j equals big T. This is a softmax function. It gives us something that looks like a probability distribution over each of the input tokens, big T. So it's a normalization of those scores we just got in the previous step. So we have sort of a weighting for every one of our input steps. Now we want to do the blending. We want to kind of combine the information from each of these input representations. These input representations are the V's over here. So all we're doing is just like weighing that each vector by the proportion alpha sub I, which we got from softmax. This is kind of like a probability, and we just sum all of that together over each of our t steps. So a little bit of the information in position 1, a little bit is represented by a small value of alpha sub 1. A lot of the information in the second position, this would be an alpha sub 2, that's pretty big, times the information in the second position, plus a little bit of whatever information is in the third position at a small value for alpha sub 3 times whatever information is in v sub 3. Okay, and all of that goes together to say this is the information in C, which is a unique combination of the inputs relevant to whatever you're looking for right now, which is this query Q, which started off this whole process. A bit of a side note, there's various forms of score functions we can use. Because the query is a vector and the keys are vectors, we could just use dot products, so the good old-fashioned dot product. Normally we use a scaled dot product, which we see down here, which is just the dot product scaled by the square root of the size, like the kind of cardinality of these vectors, d sub k. This is from Vaswani et al., this foundational paper. A lot of these papers I've pointed at, by the way, come from Canadian authors, which is nice. Nice for Canada anyway, and our great AI and machine learning infrastructure. Anyway, regardless, Badano et al., another Canadian, Yoshua Bengio, and so on. Another score function is basically this additive attention. I'm not going to go too much into how these score functions differ. This is kind of an aside anyway. It's just to mention that like how we relate a query and the keys of our inputs, there's various choices we have at our disposal, but the scaled dot product is the kind of the default in transformers. As you get bigger vectors, so with larger d sub k's, so as their size increases, the raw dot products will also become larger in magnitude, which can affect softmax because these scores are then passed into softmax. So this is just an explanation for why the scaling is used. To keep optimization better behaved, that's why this is the default. It reduces the effect of massive, the result of massive vectors in magnitude. This is a bit of a distorted image produced in Python, but I think all the important information is here. This is attention to one big picture. We have our source tokens, je suis étudiant, and the period is its own token. Each of those in our input recurrent neural network are represented by these encoder states at every moment in time. These are just hidden vectors, h sub 1, h sub 2, h sub 3, and so on. And we'll have keys for each of these. These are kind of representations like pointing to each of these encoders. And we'll have these values. And then now we have the idea that we have a query. So I'm producing a word right now. What information, so now I'm in the decoder right now. So over here we're at the decoder side. I'm producing a new word right now. I need to figure out what word to print out in English. So what information in the source is useful right now? Well, I can compute using the keys. I can compute like how much information is actually like relevant at position 1, position 2, position 3, and so on. It turns out in this case that the third position is the most relevant, so that's represented as this value k. Says, like according to the query, this according to the score over here, this is my query, and I get a high score for position 3. I produce my softmax functions, so I have my softmax function at time t of output for input positions 1, 2, 3, and 4. There's a little bit of relevance to position 1, 8% so to speak, 14% relevance in position 2, 70% relevance in position 3, and 8% relevance in position 4 in terms of my 4 input tokens. So then I can combine all of these things. I can take 8% of the information in position 1, the value is information in position 1, plus 14% times information in position 2, plus and so on and so on. This gives me a blended combination of all of these values of the information in my input tokens. This is the context C sub t. This is useful for me at time t, and I'm going to make use of that when I'm producing my next word that I'm going to produce, which in this case would be student. So just to hammer that home, in case it wasn't clear in the previous slide, every moment in time, for every word I'm producing in the decoder, I'm going to pay attention to different words in the sequence, in the input sequence. Attention isn't like one fixed alignment for the whole sentence. Every time I'm producing a new word in my decoding step, I'm going to pay attention to different things in the input. So for example, when I'm producing the word am, I haven't produced it yet, when I'm about to produce the word am in my decoder, I'll have a particular set of attentions. I might pay attention to je, 10%, suis with 72%, étudiant with 13%, and so on. Okay? So when I'm about to produce the word am, I would like the decoder, to be mostly paying attention to the word suis in the input, and then taking information from the word suis, whatever information is in the word suis that's relevant to me, I want to use it for my decoding to produce the word am. Later, when I'm about to predict the word student, like we saw a moment ago, the whole attention changes. These are all values of alpha. These are all the outputs of the softmax, like we saw a moment ago. This row is the exact same example from before. 70% of my softmax function is paying attention to the word étudiant. So when I'm producing the word student, I'm mostly using information that is encapsulated within the representation for the word étudiant. So the same source sentence, the input's not changing, can support different queries. So for every word that's being produced, I'll have a different query. This will result in different weights. This will result in different retrieved contexts. So the overall blended context vector C will be different from moment to moment when I'm decoding. And then it'll change for different target positions, for different output positions. So there are some trade-offs here with attention. So the first benefit is that, like we started off this lecture, I now have access to any position of input. Like I no longer have to have this one compressed bottleneck of information, that one context vector that comes out of my encoder. Now I can look at any information in the input and make use of it, which makes a little bit more sense anthropomorphically. Because of that, because I can pay attention to any word in my input sequence, this is going to be better for long-range relationships. I'm not going to talk too much about that in this class because this class is not a natural language processing class, but sometimes the information that is most relevant, at like the 30th or 40th word in a sequence might occur at the very beginning of the sequence. Maybe at the beginning of the sequence, that's when I introduce the subject of the big verb, of a massive verb phrase with lots of components to it. So the important information is at the beginning of the sequence, not the end. But if I kept on rewriting over and over a single context vector, I might have written over the useful information that occurred early on. So long-range relationships across wide ranges in time is not a problem anymore because I can look at any piece of the input. There's also a lot of parallelism involved, so I don't have to compute like one moment in time after the other. I can compute all of my attention kind of all at once if I parallelize everything. We're going to just briefly touch over how to represent things in terms of matrices. If I can do matrix multiplication and like matrix algebra, then I can take advantage of modern GPUs to parallelize everything. And it's very flexible. There are some costs, obviously. So one of the main costs is to do pairwise attention will be, if I have like sequences that are about length t, they don't have to be the same length, but often they'll be about the same length, then for every word of input and every word of output, this is going to be a big matrix with all these attentions between them, and this is going to be a t squared, like it's a square matrix, so I'm going to need squared on the order of a quadratic time and memory to add this new attention component. So t to the squared is not the worst thing in the world, but it's still a relatively heavy cost. I don't have position info yet exactly, so this is something I'll come back to a few times to maybe hammer this home a little bit, but we don't necessarily have positional info. I don't know that this is the first, second, third word. All I have is vectors and weights. And then when I'm combining them together again, I'm combining them together in just a straight independent sequence of terms. So there is a permutation equivariant, which is a fancy way of saying that attention is blind to order by default. I'll say that again. When I'm paying attention to words of the input, the attention mechanism is actually blind to the order. So we're going to need to rectify that a bit later. as a cost associated with it also. And because we're adding all these shortcuts, these short circuits, models can learn these shortcuts, these spurious correlations, memorize artifacts. So all of the same problems with overfitting kind of rear their ugly heads again. Just because we're adding like big attention models with these big t-squared new matrices of attention, this introduces problems. It doesn't mean it's better just because it's a bigger neural network. Sometimes people get the idea that bigger neural networks must always be better, but this is going to introduce some challenges for us. Again, evaluating on held out data, not just finding instances that match your expectations. All of the regular caveats we went over to be good scientists is part of this conversation as well. Bit of an anti-example. So soon enough, we're going to see we saw already this matrix during the machine translation example. It was a black and white matrix. It showed when I'm producing this word in the output sentence, I'm paying most attention to this word in the input sequence. I'll just go back to that now for a quick moment. I was talking about this. Okay, so when I'm producing the word Européen, I'm mostly paying attention to the word European. And here's like another visualization of it. And this kind of really matches our expectation. And because of that, we're likely to just kind of let it wash over us and not think about it too critically. Like this matches our expectations, so we're happy about that. But when things match our expectations and we're inclined to just let it go, that's when it's a kind of a bit of a blind spot, and that's where problems can happen. So we think that using this kind of visualization map I just showed you is a form of explanation. Like, look, the neural network is learning things that make sense to us. We're very, very happy. This is, I call it seductive. So it makes sense, like to believe that the neural network is learning things that we understand. This is sort of correlational. It's not causal explanation. So again, human beings, we see causality when there isn't any causality really. And so here's a little example to exemplify this. Imagine we have a model that uses attention, and it's a classification model, and it's going to classify this comment on a ridiculous social media platform as toxic. This is a negative, bad comment. So now we're in a bit of a different situation. We're not doing encoder decoder modeling, but the same idea applies. We're going to have attention that's going to look at the class, and when it's producing this class, this is a toxic comment. It'll pay attention to the words in the post, and the big attention will fall on like an identity-related word, right? So maybe this happens a lot online, as I'm sure you're aware, that toxic comments will focus on an aspect of your demographics, for example. So you'll conclude from that, like this will make sense to you. You'll conclude that the model based its decision on the toxicality of this comment based on this one word. Look at this one word, it occurred here, therefore we have an explanation for why this comment is toxic. But it's not exactly that. That word is used in a context, it's not that word by itself that's producing the toxic comment. It's more complicated than that. It's more complicated than your intuition led you to believe. So first of all, attention weights, show one possible internal weighting mechanism. It doesn't necessarily mean it'll always turn out that particular way. And we're going to see an example a bit later where the attention maps are not so clear. Different parameterizations will yield different predictions with different attention patterns. So I'll try to make that clear also, but just because this particular example shows a particular pattern, if you were to run this thing with different random seeds or slightly different hyperparameters, or just other randomness, the results can be very different. Your attention mechanism can look a little bit different. Your explanation is going to change. Like humans, we like having the one true answer for things, but that's a frailty of our squishy human brains. The downstream nonlinear layers can transform information after the attention is computed. So there's more going on in the classification, a little bit after the attention mechanism. So again, attention by itself is not the whole story. There's two papers here I want to draw your attention to, which I find is funny. There's one paper from 2019. Everyone started looking at these attention maps. Not everybody, obviously. I'm being a bit superfluous, hyperbolic. So people were using these attention maps to explain decisions. Like, look, the model is behaving this way because it's attending to these pieces of input. So people were using attention mechanisms as if they were explanations, and this foundational paper came out, Attention is Not Explanation, which I highly recommend you read. But also in the same exact year, this other paper came out. I can't read it right now. It's called Attention is Not Explanation, which is kind of saying, well, it's not It's not that it's not explanation. It's not that it is explanation, but it's not explanation. There is some value to it. You can do some kind of explanation under the right circumstances and with the right caveats. So I thought it was funny that there's two papers in one year. Attention is not explanation and attention is not explanation, both of which kind of provide perspectives on what we're talking about. So please read those papers. A better takeaway is very similar to the kind of takeaways we saw throughout this course, which is that what we're talking about right now is useful. It's not useful. It's still a useful diagnostic. Attention can still tell you something important, and it can still be helpful for overall performance, but it's not a silver bullet. It's not completely useful all on its own. You're going to need to keep your deep knowledge of machine learning in context. So a bit more mathematical depth, but not too much. Let's go back a little bit and just dig into some of these earlier ideas. This is just a quick work derivation of attention weights. So we have a query. So this query is just this vector 1, 2. So when I'm producing, I want to produce my a particular word of output. I have this representation for what I need at the moment. This is this query. It's only a two-dimensional thing just for simplicity. And then I have three inputs, 1, 2, and 3, and I have keys, 1, 0, 1, 1, 0, 2. I can do a dot product of these. So the dot product is literally just like it's the first element of one times the first element of the other plus the second element of one times the second element of the other. So in this case, it's 1. In this case, it's 1 plus 2, which is 3. And then it's 0 plus 4, which is 4. So we have our dot product scores of for vectors 1, 2, and 3. So I'm not doing any of the scaling I mentioned before. In that other example, this is just raw dot products. I can feed these into my softmax function. So you can do this yourself. This is done behind the scenes over here. So I have like 1 divided by 8 is the softmax for 1. 3 divided by 8 is the softmax alpha sub 2. And 4 divided by 8 is alpha sub 3, the softmax for position 3. So as you'd expect, the largest weight goes to the third position. Here's like the visualization of what I just did. Like 71% is assigned to the third vector, but not, that doesn't mean that I just select the third vector. This is a soft combination. So I'll take like 71% of vector 3, 26% of vector 2, and 4% of vector 1. I realize that these numbers don't actually sum to 100. They look like they sum to 101 or 1.01 anyway. I think this is like this Python that produced this is doing rounding in a way that produces these things that are a bit off. But you get the general idea. This basically sums to 100% because this is softmax. And you can kind of see this here visually. It's kind of hard to tell actually, because K3 and K2, the key vectors for the third position and second position seem pretty close, but the query Q is a bit closer to vector 3. So this is just a representation of the vectors I framed everything by in the beginning. So similarity drives the pseudo retrieval process. The dot product is a way to tell how close these vectors are to each other, by now you know what dot products are, so I don't need to belabor this point any further. So just a bit of a reasoning sketch, like why does softmax matter? Why are we passing these dot products through the softmax? So softmax, first of all, gives us something that is, it's non-negative weights that sum to 1, so it behaves a little bit more like a probability function. And if I'm going to add a certain proportion of each of my value vectors to get an overall context vector, often we prefer to have something which is normalized, which behaves sort of like a probability function, or a likelihood function, I suppose. It's differentiable, so these softmax functions are easily differentiable, which we care about because, again, we're going to pass gradients through these neural networks to do training in ways very similar to what we saw in earlier modules. And so doing so will help us sharpen or spread focus in a controllable way. If we don't have softmax, then things will be kind of unnormalized, and then we might end up with a situation that resembles gradient explosions and that sort of thing. If one softmax score is much larger, then attention will become concentrated. If scores are more similar, attention is spread out. That's the example of the right and leftmost visualizations over here. These are the weights, softmax weights, according to, in this case, 4 different input tokens. So, in the first case, I need more or less the same amount of information from each of my tokens, but in the rightmost case, there's an awful lot of relevance in the the case of one element position. It's not exactly first, so a case of one position. So we can kind of see that this selective attention based on what I'm producing at a particular point in time for my decoder. Softmax is not just normalization. It's not just that I want to normalize all of these scores. We want to sort of control the trade-off between these sharp instances and these distributed aggregations. We just basically want relative contributions that behave in a controllable fashion. So we've been talking about a thing called cross-attention this whole time. So cross-attention means we're kind of paying attention across two different recurrent neural networks. One was the encoder on the input, and one was the decoder on the output. So cross-attention, when we're producing our outputs, will help pay attention to the source, but it doesn't really pay attention to the text itself. Sometimes we don't have a translation from one language to the other, or from one modality like audio to another modality like text. We just want to represent the text itself. We want a good representation of text. So recurrent neural networks can also just read text for its own sake and then encode information for its own sake. So why do we need to restrict attention from a decoder looking to an encoder? Well, we don't. We have the cross-attention, which is what we've been talking about this whole time. We have our queries, which is related to our, it's in our decoder. So for the teeth word in our decoder, we'll have a query vector, and then we'll have keys and values for each element S from our encoder, each of our input indices. And we'll have these vectors we're going to have to learn. So the use case, like we've been talking about this whole time, is to connect the current output step to the most relevant input step. But self-attention, by contrast, every position in one sequence, when we're looking at one sequence, like one English sequence of words, will create its own query, key, and value that will pay attention to everything else in the input. So we're going to have this big weight matrix W for our queries, a big weight matrix for our keys, a big weight matrix for V's, and then for every element in our sequence, X sub I is like one word in our sequence, we'll multiply it by our weight matrices and get us a query, a key, and a value. So this basically allows us to have better internal representations, which I've been calling H a lot, for this particular sequence. Right? So for this word at time I pay attention to some different amounts to all of the words to my left and right to get a representation for what I mean at this particular point in time. So just to contrast these two things, because this is one of our learning outcomes, cross-attention, the query comes from the decoder, like the decoder or the output says, I need to know something right now. The keys and values will come from the inputs. Here's information from the source. And then the role is more or less to link output tokens with input tokens. Self-attention, the query comes from the word right now at position I. The keys and values come from all of the positions in that exact same sequence. I'm paying attention to myself now as a sequence. And then the role will be to build up better context token representations for right now. This is a side note that just occurs to me. Earlier on, several modules ago, we introduced word2vec and glove, these kind of representations of words. And then I had a map where I showed, here's all these points in space. This point represents man, this point represents woman, this point represents king, and so on. But that meant that, that word always had that particular representation. The word king always meant that exact vector representation of numbers. What's going on here is that the representation for the word king will depend on all of the words that happened before and all of the words that happened after. So each of those words will all be paid attention to different extents, and then that will build my representation for my word king at this time. So I now don't have one representation for the word king, but the position of the word king in my vector space will constantly change based on whatever my particular, what situation I find myself in, the rest of my input sequence. Normally I like thinking of the word play, right? So instead of having one point for the word play, so every time you see the word play, it means this exact thing. That doesn't make any sense because you can go to the Neptune Theater and see a nice play over there where the actors are on stage putting on a nice play. Or you could go to see the Wanderers play soccer. So they're playing soccer, or you see a beautiful play and they score a goal. There are some similarities between those two situations, but also there's a lot of differences is the main point here. So like a play in soccer and going to see a Shakespeare play, there's a lot of differences. That's not one meaning of the word play. So based on if I hear the word actor and stage and costumes, then the word play will change its meaning. If I hear like pitch and goal and like players can be both, but I guess cleats, then the word play represents something else. Its vector representation changes. So that's an important thing here. So the meaning, my representation, my contextualized token representation will change based on context. And this is a big deal for when attention was introduced in natural language processing. So I really hope that makes sense to you. So now I'm not just producing words of output. I'm having a better way to represent the meaning of myself at a particular time, and I'm doing so based on the context in which I find myself right now. The person speaking right now is a word. So cross-attention answers, what source positions help me right now when I'm producing my output? Self-attention says, what do my neighbors tell me about myself? So self-attention has all of the same kind of hallmarks we saw a moment ago. We still have our scores. Right now the score I'm representing as an E. So I have my dot product of my query and my key. In this case it's normalized, like we saw a moment ago. All of these normalized scores are passed through the softmax function to get a kind of normalized weight, alpha. This is sort of a weight between token I and token J. And then Z, sub I, will be my contextualized representation of me right now. I'm at position I. I'm a word. What do I mean? Well, I mean a little bit of, the first word in my sequence, the second word in my sequence, the third word in my sequence, all with different proportions alpha, all summed together in this sum. So row I in the attention matrix will kind of be a probability distribution or a pseudo probability distribution over which positions I consult in order to define myself. Okay, so this is a key shift from recurrent models. In the past, how I represented the meaning at time I was a combination of the actual word at time I plus a kind of a smushed together combination of everything that came before me, which was an H sub T minus 1 or I minus 1. But now it's a little bit different. Now it's a sum of everything in my inputs to different combinations, to different amounts. Here's a matrix form. This is is distorted in my desktop here for some reason, but it's still legible at least. This is a bit of an aside, but again, in real life, we put all of this as much as we can into these matrices, which can be pushed to GPUs, which can parallelize a lot of the processing for us. So a lot of what we've talked about a moment ago doesn't happen like step by step, very careful. Well, it's very careful, but it's all put into these matrices and then automatically sort of distributed for us. So the input is basically we have T elements of T words in our sequence. We have like D model is our chosen hyperparameter for like the width of our representations. So X is this big matrix which is has a row for every word, and it basically represents our embeddings, our default embeddings for every single word. We're going to have, again, as always, queries, keys, and values, which I talked about a moment ago. It's going to be a product of our inputs with our learned weight matrices, W sub Q, K, and V respectively. This gives us like what am I looking for at a particular time is a row of the matrix Q. Where can I find it is a row of matrix K. And what do I find there? That's an element of a row of matrix V. So for one head, I'll talk about heads next time, but right now I'm only kind of paying attention to like in one combination at a time. It gets a little bit more complicated a bit later, so we'll see that in the next module. But for one particular head, we have the same kind of we have particular scores. S, which we defined a moment ago, is just a matrix form of the scores. We'll have our softmaxes done row by row. This is going to be kind of our attention scores, which we call A, and then A times V is going to be our contextualized representations for every word. That's a big matrix Z. So again, S is our pairwise compatibility scores, which have been normalized here. A is our attention weights after the softmaxes. We have a kind of a probability looking distribution on every row. And then Z is our context-aware token representations. We've talked about this several times, so hopefully this kind of makes sense to you now. We have our inputs. We take our queries, keys, and values, get our scores, get our weights, and then this produces specialized representations for every word. And the specialization is based on the context of the sequence as a whole. So why is this a big deal for sequence modeling? With recurrence, again, I mentioned this before, but I'll mention it again. With recurrence, information has to continuously be compressed into a rolling hidden state. So like we talked about before, like every time I read a new word, I have to kind of push information and squish it into my internal representation. Okay, so token 1 will have an influence on token big T at the end of a big sequence, but I'll have to do that through T-1 chained transitions. And every time I do that, I risk overwriting something. With self-attention, so if I'm looking at representing, I'm trying to come up with a good personalized, contextualized representation for the word at position 6. I can say, well, the word at position 1 is very relevant to me right now. I'm speaking very anthropomorphically. So I'm going to take a lot of information from position 1, and I'm going to use that information from whatever the first word was to help me represent myself. So you can kind of skip over everything else and have this direct connection. So there's no risk of overwriting information in the first position. I just take direct use of it through my key, which I have learned points me to this vector at position 1 with a high degree with a high score. So this can all be done directly. I can interact with any other position in my layer. Actually, kind of these long-range dependencies. Like here, I have only 6, but this can extend over like dozens of possible words. And I can do all of these in parallel. So I can decide, 6 needs to pay attention to 1, 5 needs to pay attention to some other word in the sequence. I can do all of this very quickly in parallel using matrix multiplication and matrix algebra from the previous slide. This is one reason why attention works well for long-range structures. The model doesn't have to preserve and know how to preserve every useful signal through all possible chains, through all of these recurrent updates. There's not one true way to encode information. I have much more flexibility now, which is fantastic. Now, I mentioned this earlier. By default, these attention mechanisms are agnostic for individual position. So I can kind of swap the rows of these matrices as long as I do so consistently, and the attention mechanism doesn't really care. It compares the content vectors. It doesn't know that this vector came from position 1, 2, 3, 4, or whatever. It's just looking at the context vectors and their indices. You need that, I guess, but it doesn't make use of the indices when it's doing its computations. And this matters a lot. So take this very simple example, dog bites man and man bites dog. Okay, so these same three words, just organized in a different order. Okay, and the order matters a lot. Like a dog biting a man has a very different meaning than a man biting a dog. But if I'm doing self-attention, if I'm representing the word dog, and I'm paying attention to the other words in the sequence, it doesn't really care at that point whether man is before or after dog or bites is before or after dog. It's just paying attention to these representations and like how similar the representation for bites and dog and man are. Okay, so for an attention, for how we've framed it so far, dog bites man and man bites dog, will look very similar to the attention mechanism. So later on, in the next module, we'll talk about transformer models. A transformer model will have to explicitly add position information to every vector of input. So the word dog being first in that sequence will be associated with a representation for I'm first. The word bites will be associated with another representation for I'm second, and so on and so on. That can be a bit complicated, so you can't just, I'll talk about it in the next module. There are a couple of different things. There are learned positional embeddings. There are sinusoidal position encodings, which I like a lot and come up a lot in speech. And then there's relative position encodings or mechanisms as well. So self-attention is very powerful because it's so flexible, but we're almost too flexible. We're going to need to anchor things a little bit. We're going to need to anchor each of our individual words in big X by their positions. Because again, language is ordered, audio sequences are ordered. Usually when we're dealing with sequences generally, the order matters, and because we have such a general purpose model, we lost that. So we're going to come back to that a bit later in Module 53. A quick computational comparison. We talked about the computational complexity. In recurrent neural network models, the complexity is big O, big T times D squared for sequences of length T. This is sequential over time. Because I mentioned this earlier, a self-attention layer can kind of pay attention to every input can pay attention to every output. And this is literally a square matrix. If you're doing self-attention, you only have a sequence of length T. It's still going to be quadratic in T. So this is a dense attention over all possible token pairs. That's our attention matrix. You have to do this a couple of times, so there's a hidden constant over here. But big picture, this is the kind of complexity of the recurrence in RNNs versus self-attention in the attention mechanism. We're going to need both of these in a lot of cases. So just wanted to mention that. There's a little bit of a treatment of complexity, and attention is all you need, this foundational paper on attention mechanisms. There is one reason transformers excel for medium-length sequences on parallel hardware, like ROCm-enabled AMD hardware, or CUDA, I guess. But for longer sequences, it can be challenging, so there's all kinds of specialized ways of computing attention, using sparse, linear, or chunked attention for very long contexts. And here's a paper that describes efficient mechanisms for doing this sort of attention. Let's see some examples. So we're going to go back to the very basics, the very small level, and we're going to build a simple query key value attention for a very short token sequence. We kind of saw an example of this earlier anyway. This will allow us to inspect attention weights in a table and a figure, so you can visualize things. And we're going to hopefully see the design choice for where the query comes from. So in this example, everything's hard-coded here. We have the tokens the animal did not move. A bit of natural language for you again. The is what we call a function word. There's not no content, but there's low content. Animal is a content noun, and so on and so on. So in this cartoon example, these embeddings are represented by just two-dimensional vectors, and we've just arbitrarily written them out this way, just for simplicity. We want a neural network to basically classify as, whether an action occurred, like did something happen in this sequence of tokens. So did an action occur? Cares about the content in a embedding. So we have these sort of cartoon examples. This is the query vector. That'll help us answer this question. What matters for deciding whether an action occurred or not. So we have our key values, our vectors. These are the same values as x. Our scores is a dot product of the keys and the query. Again, this @ sign is a special Python operator for dot products in a matrix. The weights are softmax, so it's just the exponent of our scores divided by the sum over all of the exponents of the scores. The context vectors is those weights, the softmax weights, multiplied by our representations v, their values. And these are our contexts, and we're done. It's as simple as that. We're just going to show everything out in our pandas framework. We have our tokens, move, animal, not, did, the. We have our scores. So here we've sorted by score, by the weights. I guess the order will be the same, and by descending. Anyway, so move is the most important token to tell us whether or not an action occurred. Animal is the second most important, and so on. And here's the normalized weights on the last column. Here's a visual representation for what we just talked about. Each of the representations for the animal did not move will be represented by these vectors. The query, did an action occurred, will be represented as another vector. Which vectors are closest to the query? Well, it seems to be animal and move over here. So these are the dot products, how close these vectors are together. The closeness is represented by big values in the dot product. And then we can normalize by the softmax function, and we get this resulting attention distribution. A uniform weight across all of the inputs would have been this dashed line over here. So you can maybe ignore things that are less than that and pay attention, so to speak, to the ones that are bigger. So move and animal are the input words that matter most to the decision about whether or not an action occurred in this sequence. That's more or less it. So we're done. What can we take away from this? The query vector aligns most strongly with content-like tokens like animal and move. Functions like the and did do not matter so much. I'll come back to this in a second. The context vector, the overall context vector is going to be a weighted blend of all of these things. So to answer my question, I'm going to have a little bit of the, a lot of animal, a little bit of did, a little bit of not, and a lot of move. All of those things combined will be a new vector that I'll pass in to towards my output to make my decision. Did an action occur, yes or no? If you change the query vector, this is going to change what the model retrieved. So if my question was different, then this query vector will be different. It'll be more or less similar to different words, and that's going to result in different representations on the output. Attention is task conditional. It depends on what I'm doing right now. So again, like I talked about earlier, the attention weights will keep on changing depending on what I'm doing. The important thing, which is what I wanted to mention a moment ago, is that I don't want to say that these, I've made a decision here, like I'm only going to say animal and move matter. No, about 26, a bit over 30% of the overall information in my context vector comes from the words the, did, and not. So I'm getting an awful lot of information from stuff that is not animal or move. So that's the main thing. It's not like I'm making a deterministic choice to use information only in animal or just animal and move. It's still a weighted blend of things. I wanted to point out, this is a cartoon example I put together just for the sake of explanation. But after doing this, I realized that, well, you could say, the question did an action occurred. The word not probably matters quite a bit, So like the animal did not move. The answer should be no. There's no action being undertaken because of this not word. So this query, because of this query, I should have paid attention to some extent to the word not. For whatever reason, the way that I've learned these query matrices, W sub Q, which you saw a moment ago, like the way matrices right now, I'm just like taking it as read that I've learned how to represent them. I've learned how to pay attention to things like animals and movement. So my query vector ends up being in this position over here. But another way to pay attention would have been very attentive to negation. In that case, the query would have been way over here towards not and said, no, if you want to answer the question, did an action occur? The main thing you need to pay attention to is not. Neither of those two approaches is correct on its own, but I can't easily do both of those things at once. So right now I have one kind of head. I can pay attention to one thing or the other. Right now I'm paying attention to things like animal and move, producing this kind of attention distribution. But another way of looking at things would have had this query vector over here to the left. I would have needed another head to pay attention to that. This is again getting a bit ahead of ourselves, but so far, just to keep things simple, we have attention mechanisms, just only one. We have one attention mechanism. But I could have different ways of looking at things, like I mentioned a moment ago, and those different ways of looking at things would require different heads, different matrices that focus on different things, set the query vector in different positions, and then a combination of all of those different heads would matter to my overall answer. So it's a bit more complicated than I'm referring to here, but I wanted to keep things as simple as possible, but not simpler. Let's see a worked example where we actually do some metric-related predictions. So we're going to go back to GRUs, which you saw in a recent module, and we're going to compare this with self-attention on a synthetic long-range task using toy data, but something that looks very similar to the kind of task we saw earlier. So our input is going to be a sequence of integer tokens of length 30, and our label after those 30 tokens, I just want to say, if it's going to be a decision 1 if the first and last token are the same, and if they're not the same, output 0. So it's a classification task, and it depends on whether the first and last token are the same or not. Super easy. Okay, but I have a very long sequence of numbers, and as I'm reading all of these numbers in a GRU, in a left to right recurrent neural network, I'm going to be overwriting my context vectors, and I'm going to start forgetting that first number I saw in sequence, making the answer to this question more and more difficult the longer and longer these sequences are. So this is helpful for us in this particular example because the information that's useful is in very different positions. I have long-range dependencies. The sequence can still learn this, but because I'm going to have to keep on pushing information through each of these forward connections in the GRU, it's longer. And again, I mentioned this a moment ago, I might overwrite it, but at self-attention, I can have a shortcut directly from the representation of the last number to the first, and then I can use that to answer positions directly and ignore everything that happened in the middle. So this is synthetic. Again, it's a toy example, just like the one we saw a moment ago, just to try to get these ideas across. So it's very simplistic. It kind of represents things that happen in real life. So occasionally you might have a sequence like the sushi that your brother's friend's girlfriend's aunt's teacher's wife told you was good was actually tasty. It's a long sequence of words, and the tastiness at the end and the sushi at the beginning of that sentence have a connection to each other. So it does happen in English sentences. But anyway, right now we're just dealing with sequences of numbers just for simplicity's sake. So we're actually running an experiment. There's a lot going on here, which I'm going to leave it to you to look over just for the sake of time. But I produce my data. I have like a vocabulary of possible numbers. I have a sequence length of 30. This is what I want you to play around with. So change this to 5 or 6 and see how the outputs change. Change it to 50 or 60. It's not going to change much, a spoiler alert, but you can change the sequence in time to see how much better self-attention is going to be. The dimensionality, how well we represent ourselves with these vectors. This is the size of the hidden states. That's 16 in this case. You can change this if you want to. I make my balanced data sets of different sizes. I push them at some point to the device, I hope. Can't remember. Anyway, it doesn't matter right now. I create my GRU classifier using just PyTorch's GRU, and I have the linear output because I'm doing classification. I have a tiny self-attention over here, so I have embeddings and a bunch of linear layers. The details here don't matter to you. I'm not going to ask you to encode a self-attention mechanism by hand, but this is just like we saw all these components a moment ago, like our softmax with these dot products. You've seen all this before. This is my tiny self-attention network. I do my evaluation, I do my training. This is where I actually create the GRU and the self-attention network, actually do the training of each, and then summarize the results. And so this is where the decisions are. I was just curious for a moment. So like the value of position 0 and the value of position end, which is 30 in this case, or I guess 29, but it could be, if you change the length of the sequence, this just points to the ends. Anyway, if these are the same, then it's a 1. If it's different, then it's a 0. All good. So spoiler alert, the GRU got a test accuracy of 50%, and the tiny self-attention got a test accuracy of 100%. So quick spoiler alert also, I've cheated a little bit because I have embedded positions into this decision. So my representations for every word is every token is an embedding for that number. So it's an embedding for that input X, but it's also that plus my representation for the position I find myself in right now. So I mentioned that earlier, that because attention mechanisms are agnostic to position, you're going to have to kind of anchor every input token with its position. its position is represented here by self-pos positions, and I'm just concatenating these things together to represent my overall embedding. So I'm kind of cheating a little bit. I know the neural network knows this number comes in position 1, this one comes in position 2, and so on. It's not really cheating that badly. It's just it's cheating in the sense that we didn't talk about position encodings yet, and we're going to talk about that in the next module. So I'm kind of like stitching something from the next module in, but that's fine ethically, because normally when we see attention mechanisms, we also have position encodings as well. So nothing untoward is going on. It's just that we haven't seen that position encoding yet, even though I mentioned it. So here's the learning curves over the epochs of training, over 35 epochs. Solid curves are training, dashed curves are validation. We called test a moment ago. So both approaches start off about 50% accurate. This is like a random, like, do they match or not? It's a 50-50 chance because it's balanced. I skipped over that before, but half of the time the first and last tokens are the same, and half of the time they're not. So it's a 50-50. There's no problems related to class imbalance or anything like that. Both of them start with 50-50 chances, but very quickly the self-attention mechanism learns to say, well, the thing that matters when you're making a decision at the end of your sequence is to pay attention to the first element in the sequence. It learns that very quickly. You can see this very quick spike in performance, in accuracy, in both training and validation, because it's learned the trick here, and it's just going to be 100% all the way across. I think I mentioned earlier that normally when I see 100% in reports, I'm like, something sketchy is going on over here. There's some shortcut being taken, but this is a toy example. The neural network has learned the trick, and it learns so very quickly. And congratulations to neural networks for doing so. The GRU has kind of learned something over time. So gradually over time during training, it has learned a little bit of something about these sequences. It has learned when I see this number at the beginning and I see this sequence in between, then I'm learning that this is 1 or 0, they match or they don't as outputs. But this doesn't really help you in new test data. It doesn't generalize very well to other sequences. It's not able to pay attention, quite literally, to the beginning of the sequence and remember and have a shortcut to that point in the sequence. This is constantly overwriting itself as it's reading these sequences, and it has learned to try to remember what's at the beginning, but it's going to forget over time because it's crammed in so much extra information into its little head over time. So and it doesn't generalize well. So the testing is still close to 50%. I like this example because even though it's learned something meaningful, it doesn't generalize well in validation. So this is a nice pedagogical thing. Look how great self-attention is. There you go. That's basically the moral of the story. We can look into the attention weights. So when we're, here's the weight matrix we saw before. The rows are the query position I. So when I'm representing the 0th, the 1st, the 2nd, the 3rd, 4th, 5th, blah, 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 blah. When I'm representing the tokens at that moment in time, I can pay attention to different elements in my sequence. The diagonal is usually pretty hot. Like when I'm representing myself, I pay attention to myself. So you see kind of big values along the diagonal. In each of these cases, these are for two different cases. The case on the left is for where there's a match. The input is 7, the output is 7, or the first element is 7, the last element is 7. The negative case is where the first element is 1 and the last element is 7. There's no match. The decision is 0. And then the amount of attention here is the value here is how much is paying attention to these elements. So when I'm producing the 30th element, the element at position 29, it's paying an awful lot of attention to the information in position 0 because it matches and it makes sense. Now, when I'm trying to do so for the negative case, so the 30th element is 7, the 0th is 1. They don't match up. I don't want to pay attention to that first element because it doesn't match. So you can see over here the weight is very close to 0. There's no correspondence between these two things. And then that information is the key information that my classifier linear layer uses to make its prediction. No, it's not a match because in this particular toy example, this little kind of pixel over here is the one to pay attention to. If it's on, they're the same. If it's off, they're not the same. And I've taken a shortcut to answer my question through the attention mechanism itself. So there's a couple of things going on. Both models start with 50-50 chance, which is nice, and which I mentioned earlier. This tiny self-attention model quickly learns this kind of hack to solve the problem. And it converges faster because it can shortcut the 29th element and the 0th element directly in one layer. I've not talked about stacks and stacks of these things, but I can have one attention mechanism in the first hidden layer, and that leads into another one at the second hidden layer, and I can stack these things on top of each other as well. The GRU struggles in this particular example because it has to compress the first token's information or signal through all of these recurrent updates, so it has the challenges we talked about before. This is kind of consistent with the idea that GRUs, LSTMs, or RNNs generally, they're especially good for short interaction paths, but the longer things get, the harder it is to maintain these long-term dependencies. This is, be careful, this is a synthetic task which isolates a very particular hack. Like we set up everything with an easy hack that you can learn in one step. In real language data, GRUs and LSTMs are still going to work a lot better. Things in real life aren't so direct as this. So this is not to say you can throw away GRUs now. I need to emphasize that over and over again. Every time we introduce a new idea, it's not like, fine, we've solved a problem in an old method, now we have this new thing. That's not true at all. You have a very wide tool belt of all these different things you can use in different situations. GRUs and LSTMs are not obsolete just because attention mechanisms solve some problems or have interesting properties. I mean, one thing is self-attention cost means that sometimes self-attention is way too costly for the problem, and the cost doesn't justify the benefits. So the self-attention reduces the interaction path because I can shortcut these two things directly. Instead of having to push information through T steps, like an RNN, I can take a shortcut in constant time from one directly to the other, which was what this paper talked about. What it doesn't show is, this accuracy works very well on the synthetic benchmark, but don't think that this model understands sequences generally. Like this is a very particular example. If I were to take this attention, like these weights that I've just learned, and apply it to another task where I have to pay attention to whether or not the second token in the sequence matches the output, I'll have to kind of learn a lot from scratch. It doesn't generalize very well to different tasks. And so on. Sometimes these metrics can look good, but overfitting is still a challenge. Attention plots can be plausible but not robust. I'll talk about that in a few moments. It can fail for variable lengths. So right now, every input sequence is going to have length 30, but if the input sequence has different lengths, maybe it's not going to perform as well. Training can depend on initialization with pooling choice, so play around with the hyperparameters I set and see if you can't get GRUs to perform more similarly in terms of metrics to attention mechanisms. All of this is to say that, again, reinforcing this idea that architecture matters, but the objective matters, the evaluation matters, and all of the elements of that evaluation also matters to your determination and your understanding of these systems. So attention models come with familiar-looking risks. If you're using user data or if you're using this kind of model in a high-impact scenario, be wary of bias amplification, especially for large text corpora that might contain some stereotypes. Attention not only does attention not remove them, but because of now these shortcuts that exist, if an overall machine learning architecture can learn that by paying attention to race, for example, I'm going to get better results on average, that's going to be bad for people. Attention mechanisms are more parameters I'm layering on top of my existing architectures. The more parameters I have, the greater the risk of memorization, which is going to be a problem for privacy. Interpretability. So stakeholders overtrust attention. I think I'm going to talk about this again in a moment. So if you have these heat maps, and again you say, well, look, there's a lot of attention being paid between these two elements. Like a lot of attention is being paid to my face right now, so I'm going to zoom out. There we go. Then this can be misleading. It can lead people to overtrust attentions. I'll come back to this in a second. And then shortcut learning is, of course, a problem. So attention is not explanation. So despite the two papers I talked about before, attention mechanisms are not the same thing as explanations. These are not causal relationships. Attention can be misleading. You can construct the data in a way that the models are going to pay attention to certain elements of the inputs in a way that's adversarial, in a way that you can fool people to believe certain attention patterns that might be not great. I see this is not hasn't been compiled yet, so I'll try to compile this in. This other reference. So when you're deploying these attention-based models, you always want to do the same kind of caveats. Do stress testing, look at subgroup performance, look at counterfactual inputs, and don't always be curious. Why did it matter historically? So before transformers started to dominate, and who knows what the next architecture is going to be, but for a long time, encoder, decoder, RNNs, for machine translation, for speech recognition, they dominated, but they struggled because the decoder had to rely on these single compressed encoder summaries. So all this information had to be compressed, and that was difficult and problematic in various ways. And now attention solved that by letting the decoder revisit like any element of the input it wanted. Why don't I have access to the input? That was the whole point of this whole module when we started off. So that's a big reason why attention has mattered for the past 10 or so years at this point. Or greater than 10 years, certainly. So this is a conceptual shift, but I want to point out that this actually is very closely related to this concept of alignment. So before recurrent neural networks, even in the 90s, IBM had a model of taking information from one input sequence and then mapping it to an output sequence, and then kind of paying attention when I'm producing the word Européen. The word European matters more to that translation. So we had this alignment, which was actually performed with expectation maximization, if I recall correctly. And you saw these maps, which are very similar to that purple-looking map between English and French words we saw earlier in the sequence. So everything that's old is new again, and these concepts of alignment may or may not have influenced the idea of attention as a means of improving encoder-decoder models for machine translation. But certainly RNNs, even LSTMs and GRUs compressed information to one state. Technically, it could be two states, a cell and the hidden layer for LSTMs generally, but it compresses information at the end of a sequence, and now we don't have to worry about that anymore with attention. And this generalizes very well beyond translation, like we talked about earlier. For example, it can apply to language, including both text and, for self-attention, text representing itself, maybe being used for classification, chat systems, machine translations. You can think of chat as kind of a machine translation. Instead of taking an English sequence and then producing a French sequence that represents that English sequence, you can take an English sequence and then you can decode the best possible response to that input. And now you have an English input to a chatbot and then English output from the chatbot back to the user, and go back and forth. The same encoder-decoder model, or seek-to-seek model as they call it sometimes, can be applied in both situations, and attention can help you out in all of those contexts. Speech we talked about earlier, so taking audio inputs and mapping them to phoneme or letter outputs can help you with speech recognition. I wanted to mention vision. So vision, in particular multimodal vision, can combine a modality of images and a modality of text. And you can combine these two models together with attention mechanisms. Again, use two sources, and you can use the attention, when I'm producing the text of a caption for an image, what pixels in the image should I pay attention to that are most important for me right now when I'm producing my word of output. So in a decoder that's producing a woman is throwing a, right now I'm going to produce a word. This word depends on what I saw previously, so I'm in my decoder model. But I want to pay attention to the pixels in my image, across modalities. This kind of light over here represents the attention being paid to different pixels, and you can see it's paying attention to this area of the image. So there's something going on in this area of this image which is important to me when I'm captioning this image. So I'll pay more attention to that. Again, that's speaking very anthropomorphically, but something about those pixels produce representations. Those representations are directly fed into my decoder, and my decoder puts out the word frisbee at this point. So paying attention produces much better captions. and so on and so on. So producing a caption for this image over here, the attention mechanism from the decoding text pointing to the encoding image will pay attention to this region of the image, and then it'll help me produce a nice, really accurate or correct word stop for this caption. A stop sign is on the road, etc., etc. So isn't that great? You can pay attention across modalities too, not just text, but in images and so on. This particular example comes from this famous paper, consisting of a whole bunch of Canadians. So quick point, Module 52, this one, and Module 53, the next one, are deeply linked. They're both highly connected to attention. So today we introduced query keys and values. We differentiated cross-attention and self-attention. So cross-attention is like input encoding and output decoding. Self-attention is like representations of my sequence in terms of itself. So yeah, we talked a little bit about self-attention as token-to-token interaction. The word play changes its representation based on the tokens around it. We talked a little bit about the strengths and the trade-offs of attention-based mechanisms relative to recurrent neural networks, relative to recurrence. In the next module, we talk about multi-head attention. I mentioned this a little bit in example 1. Remember I talked about, well, to answer the question, is something happening, I paid most attention to animal and move. And so one way of looking at things, one way of paying attention, had that query vector in that area. But another way of looking at things would have focused on negation, and that would have required another head, another attention mechanism to pay attention to different things. So I'll need multiple attention mechanisms. These multiple attention mechanisms will be multiple heads. We'll talk about that next time. We also hinted that we needed positional encoding. I needed that for example 2 to work as well as it did. So I need to say this word comes in position 1, this word comes in position 2, and combine all of these things with my input encodings. We'll talk a little bit about feed-forward sublayers, so kind of feeding these mechanisms, like these entire blocks, just not as one thing, but as we'll have many attention layers all stacked on top of each other. The name of the game in neural networks is to keep on stacking things. I think we'll see residual connections, at least very briefly, and some layer norms, like we saw in RNNs and CNNs not too long ago. So you need normalization. And that's basically it. We're going to have these architectures now, which have a lot of subcomponents to them. And these are going to be transformer blocks, which is sort of the where most of the community is at now in terms of deep neural networks. Here are some quick conceptual checks for you. Here are some, but not all, of the references. Thanks as always for watching. See you next time.